and thanks a lot for your acceptance of this invitation, which was a very short notice, and you really helped us and bailed us out during this particular crisis issue. Dr. Ghanapriya is actually an assistant professor in the Department of Electronics and Communication Engineering at NIT Kurukshetra. Uh, and she joined recently in November 2022. But prior to this, she was assistant professor at the Department of Electronics Engineering at NIT Uttarakhand, and she was there since 2013. She has received the PhD degree in the area of signal processing from IIT Delhi, and her project was actually based on the ST microelectronics in collaboration with that, which was in California, USA. And the work that she carried out was actually showcased in one of the biggest consumer electronics show in USA. Uh, because of the novel work and original contribution, she has been awarded 5 US patents and a European patent. Uh, and she has worked on the funded project from the Ministry of Electronics and Information Technology and Department of Science and Technology, Government of India. Of course, being an excellent researcher, she has got a lot of publication in very high impact factor SCI journals. And currently, she has got interest in image processing, speech processing, signal processing for IoTs, and in deep learning. So she will be talking about the application of deep learning in this particular area of automation, and she will give you some more insight into the deep learning and how it can be used. So thank you, ma'am, for your time. And this is an odd time again, but I thank you with the deepest of my heart that you have taken time out at this odd juncture. And of course, I am sure that the participants over here will be benefited from your experience that you had during your PhD and after the PhD, the research work that you have carried it out. Thank you, and the floor is yours.
Thank you, sir. It is really very kind of you to give so humble words and kind words for me. Thank you. So now I shall start my presentation.
Yes, please.
Is my screen visible?
Not
No,
yet.
ma'am.
Yes, it is coming up now. Yeah,
Okay.
it's visible now.
Thank you. So I shall start with deep learning. So at the first, we shall talk about the introduction and what is the history behind machine learning and deep learning in speech technology. Then we will be going deeper into what is deep learning, what are the short explanations of CNN. I shall be talking in detail about CNN and its architecture and few case studies. So let us go on with. So when you're talking about speech introduction, you have been learning a lot regarding your speech technologies. There are quite a few papers which discuss in detail what are the machine learning paradigms that are available, and few good survey papers are also available which talks about what are the loss functions, what are the training data, what are the different representation ways. So in this we will be talking majorly about deep learning. Now when we talk about speech technology is very old research area, and the neural networks which was being used since 1988 till 2007, the it was first it gone on with HMMs, then it went through recurrent neural networks, then neural network nonlinear predictions, then bilinear recurrent neural networks, neural network tandems. So these are few papers, and like you can see, at first, the machine learning models were mainly the speech recognition technologies were mainly focused with machine learning algorithms. But then there were more, we got over the problems and issues that were more relevant in shallow learning, and we went for deep learning algorithms. So deep learning algorithms are one of the most recent advances methods for achieving your objectives in your speech technology. So when I'm saying deep learning, so what is deep learning and what is so fascinating about it? So when you have heard about machine learning algorithms, they are generally relying on human design based feature representation. And then the machine learning algorithm just becomes an optimizing weights algorithm which makes a final prediction. But what deep learning has? Deep learning has the capability to automatically extract features. So it terminates the need for human designed features, thus reducing the errors. Apart from this, deep learning algorithms also has it has a way of representation of multiple layers of data representation. So let us take a small example. Suppose I have a photograph, I have an image. The image is represented by some pixels, and these are raw input data. But like nowadays, whenever you are going in for captions, and it is able to recognize what it is available in that photograph or picture, a very high level representation is there. So in that image, you are able to recognize what is a person, what is the pose in which, what is the background of the person, and all those things. So there are various. So going from bottom to top level representation, in the bottom it is extremely raw input vector representation. Then you go in for slightly higher level representation, and deep learning algorithms are able to represent at these various levels. So if you extract features, if you extract the layers in different deep learning algorithms, you will be able to evaluate representation of various levels, whether you want a slightly higher level representation, or you want a very high level representation. Deep learning algorithms has these capabilities. So now when we are talking about deep learning, let us start with the basic algorithm, and one of the basic algorithm is convolutional neural network. I'm going to explain the CNN in very short. So now, because CNN was first implemented on image, so I'll be explaining through image section only. But now you will say that how is it useful? You can use it on various algorithms which can have your spectrogram. If you just want to implement CNN in two dimension, if you are able to understand CNN in two dimension, then you will also be able to understand CNN in one dimension. Once you understand how it is input, the next layers for all the, whether it is one dimension, two dimension, all the layers, then you can easily understand the representation and its dimension. So let us go step by step. So, like I said, the CNN was first implemented on an image. So, I shall be taking an image, and then I'll be understanding how we are able to predict or classify or represent in various levels without any human intervention. We are altogether removing any human input required. Once you train a model, once you have inputted how many layers and what sort of algorithm is there, there is no need to extract human features. So let us consider an image. Now, in this image of a bird, there is a beak. Now, there are, instead of detecting a whole bird, now if we say that there are two different kinds of bird and those two birds are totally different from each other, but what I want a higher level representation. This is my expectation. This is my output which is required from the algorithm. So what will be there, instead of taking learning each parrot, if I say that I want to learn small patterns rather than the whole image, then it is much more easier to understand. So for example, for this particular bird, there are few patterns. Like, I'm going to first detect a beak. So I want a beak detector. And these regions can represent small region with fewer parameters. So let us start one by one. Like the word said, convolutional neural network. So CNN is a neural network with some convolutional layers and some other layers. A convolutional layer has a number of filters that does convolution operation. So for ease of understanding, I'll say that a filter is there in between. It is convolved with an input and then we have an output. Okay. So instead of beak detector, if I have said that I want to detect a vertical edge, or if I say if I want to detect a horizontal edge. So all those filters, various type of filters are already available in the library. So let us start. What does it mean by convolution? We all know what is a convolution. We have already studied it in our basic engineering course. So for example, I have a 6x6 image and I have a filter. This particular filter 1 which you are seeing, it is able to detect a diagonal edge, whereas in filter 2 it is able to detect every vertical edge. So whenever I'll take one particular filter, like I said, in a library there are multiple filters that are already available, and I'll take one filter and I will convolve it with the image, and then I'll have an output. So whenever I'm saying that these are the filters, so these are the filters, these are the network parameters that are needed to be learned. So now I have each filter, and each filter has a dimension of 3 cross 3 cross 3. Now I'll convolve my filter 1 and I'll go and I'll superimpose on my input image. Now what will be the dot product of this? 1 into 1 plus 0 into minus 1 plus 0 into minus 1, and so on and so forth. So what is my answer? Like, all the points are 0 and I am having only one diagonal, so the answer is 3. Likewise, I'll take, now there is also, I'll be showing you coding also if time permits. Then there will be a stride. Stride is how much we are scanning, how much we are taking a stride. So this is one stride. Then I again do the dot product and I have the answer. If I have said we are taking stride is equal to 0, stride is equal to 2, then if the first one was this, then I would have escaped 2 columns and my 2 stride would have been this. So these would have been an answer. So let us take the answer of stride 1. And likewise, if I'll scan, I have this whole answer. Then, so this are the, for this network parameter, this filter 1, I have this particular answer. Now, like you can see, because this filter was detecting only diagonal edge, so it was able to get the highest value for those values. Like you can see in the output, the highest value is 3 and the next highest value is 3. For both of them, it is in the diagonal, in the corner. Thus, your filter was able to detect a diagonal edge. Then again, I have a filter 2. Again, I'll do the same thing and then I'll have the output. Once I have the output, again you will see that these answers, the highest was only for those answers which was in vertical. Like there was no vertical, so that is why I have the only one vertical was that the last box which I am displaying right now. So the answer for it, 3, it is the highest for that. So these are the feature maps which you have obtained. What was the input? 6 cross 3, 6 cross 6 was the input. What was the convolution? It was done using filters. Those were the network parameters that had to be learned. And what are the feature maps? These are the feature maps. So we have obtained, for two filters, we have obtained two 4 cross 4 images. Again, if we had talked about an RGB image, so it would have been 3 channels. So for 3 channels, there would have been three particular planes, and for each particular plane, there would have been particular those dimensions would have been repeated with the filter. So again, I have those answers, and I will flatten them to a particular line. Again, only if I say that I have a fully connected network. So, what does it mean by fully connected network? All the inputs are connected to your next layer. So, now again, I'll be inputting this, but I do not want fully connected network. Why? Because there are so many parameters. I want to reduce my parameters. Fewer parameters are better for me. So what will I do? I will drop out few of these parameters, and then we can be having those. So my when I say CNN, what are the various levels? The whole CNN will be, first there will be convolution, then there will be max pooling. I'll be talking about max pooling. So what does max pooling does? Max pooling, out of a particular 3 cross 3 matrix, it will take out the maximum value. So instead of 3 cross 3 values, 3 cross 3 means there would have been 9 parameters. So instead of taking 9 parameters, I'll just pick the highest value. Again, if I say that I have a average pooling, so what does it mean? Average pooling means instead of taking 9 parameters, I will take the average of all the parameters. You would have guessed by right now that instead of taking 9 parameters, I would have taken the minimum value out of all those. So usually in CNN, max pooling is done. So what we have learned till now? We have learned that there is a input image. For this particular example, I am showing the cat image. That is an input image. Then what do? Then you do convolution and max pooling. This convolution and max pooling is repeated many times. You can do that many times. After that, it is flattened. What does it mean by flattened? Instead of showing into matrix format, if you just flatten it and put it in an array, then it is called as flattening. And after flattening, there could be fully connected feed forward network. Now, instead of using, okay, so yes, what is max pooling? Like I said, if this is a filter and these are the parameters. So instead of using for filter 1, I am having 4 cross 4, that is 16 parameters. So I'll just make a box of 2 cross 2, and instead of that, I'll just pick out max pooling means the maximum value. So out of those 3, I'll be taking 3. The next box, you must have guessed what is the highest value? 0 is the largest value. So likewise, instead of taking 16 parameters, we are just using 4 parameters. Thus, we are able to reduce the number of parameters. You must have guessed that there, in a particular image, whenever you are learning, there cannot be only 1 or 2 filters. There would be multiple n number of filters. And for each n number of filters, if you give a standard photograph which you have taken from your mobile, the pixel is quite large. The pixel size is quite large. Then how can you compute it on real time basis? For real time basis, you will be using this max pooling, and this is a established methodology. So again, you have done pooling. So now the question comes, will the pooling change the object? So it will not change the object. Why is it so? For example, if you do an decimation, even though the number of samples are decreased, or if you do the sampling period is reduced, even though the intrinsic information is missed, but you still have the skeleton. So this sub sampling pixels will not change the object. That is why pooling is able to reduce the number of parameters, as well as it is able to reduce lessen the number of parameters. Then a CNN compresses a fully connected network in two ways. So what are the two ways? Reducing number of connections. Okay, how are we reducing number of connections? By dropout. Then second, shared weights on edge. We can share the weights also. Then max pooling. Max pooling further reduces the complexity. So that is why in the earlier when we started off with this topic, we were having 4 cross 4 matrix, that was 16 weights. Now we are having 2 cross 2 images. This is a new image, but this is a smaller image. So in the previous one, we were using only one block, that was convolution. Now you are using two blocks, convolution and max pooling. So now, like we said, this convolution and max pooling, after that we get a new image. Upon that new image, again we are repeating convolution and max pooling. This is smaller than the original image, and like I said, if you have number of channels or more, then the number of channels is the number of filters. You'll have to equate. You have to take into account the dimensions also. After that, once you do the flattening and fully connected or a dropout layer, you can differentiate whether it is a cat or a dog. So when we are talking about, if there was a model was trained in the first slide, I had said that we can obtain abstract, we can have a representation of different levels. So let us take an example in which instead of words, if I'm able to take out features, for example, if I'm able to take out the uh, segmentation, where is the car, where is the road, likewise different representation levels. So let us take one example. Now you need to have a classifier in which you need to differentiate whether it is a car, it is truck, it is aeroplane, ship or horse. This question is for a 5 class classifier. Now when this image is input in the first layer, convolution, you can very easily see there are different filters. For example, here at least 10 filters have been shown. Those 10, after if you just print out the output of those 10 filters, what is that answer? Then the next term is ReLU. This is an activation function. Rec- Rectifier linear unit. So this activation function, just if the weights are giving you the answers in minus, so actually in minus there won't be any value in image. So you apply ReLU, and after this activation function, you are able to have that image again in a correct format. So these are the various steps or various representations which you can obtain. Similarly, when you have an architecture, just take printout of at each stage and you can have your output. So because this model was correctly trained and all the weights and were correctly computed, that is why the classifier is able to classify that it is a car in a correct format. So once we have learned the basics of CNN, now let us go deep into architectures and algorithms. So because this is a very recent and important topic, so there are a few established architectures. So this CNN was first established and first results were came out in 1998, and after that, like you can see, in 2010 there were shallow architectures. When I say word shallow, it means there are few number of layers, 3 layer, 4 layer, 5 layer. But when you were computing in shallow layers, there was stochastic gradient issue. Then that issue was overcome, and then we were able to train deeper. We were able to train using more number of layers, 8 number of layers, 19 number of layers, 22 number of layers. Then it increased even to up to 152 layer. That is revolution of depth, and it has not been very far away. It has not even yet been a decade. The number of layers has been increased. So today we are let us just discuss about these basic architectures: LeanNet, AlexNet, VGGNet, ResNet. These are very basic CNN architectures which are established. So before going through what are the architectures, how are we able to say that yes, these architectures are good? So there is an established state of art data set which is called as CFAR 10 data set, and this data set has these numbers of images and classes per images, and this is a well established. If you are an coder, and if you want to form your own coding algorithm, and you want to say that and prove that this algorithm is better than your previously stated algorithm, then this was the parameter which was used, this was the data set which was used to take into account what is a better architecture of CNN. So likewise you can see that accuracy of detecting 10 classes was achieved up to an accuracy of 95% using these architectures. So let us just fast quickly go through different architectures. Like you can see in AlexNet, the input is just in the lowest. After that, there is 11 cross 11 convolution. After that, again convolution is done, then pooling is done. So this is an established architecture for AlexNet. means fully connected. Softmax means a probability distribution is given. Instead of giving hard deadline and hard decisions, the probabilities are given. So fine, AlexNet. Once you understand what is AlexNet, you can very easily talk about VGG16 also. So what is VGG16? Again, there are various convolution layers and pooling layer, and the name itself implies that there are 16 layers. Okay. Now the number of parameters that are calculated, it is mind-blogging. 138 million parameters have been computed. So usually when we are deep training, usually it is done on using various GPU also. Few shallow means I'm not talking about shallow. 16 to 16, even up till 50 parameter, 50 layers. Those architectures, those algorithms can also be run on your computer. But to have a faster, you usually require GPU. So there is a availability of a Google Colab, and on Google Colab, it is an open platform. You just need a Gmail account for it. You are able to use your Python libraries upon it also. There is a Jupyter notebook. which is freely available. You can very easily write text as well as code upon it, and you can use GPU, which is available on cloud also, to compute this. So, likewise, now we were talking about architectures. Let us go back to the architecture. So, you can see your VGG16 architecture also. You can see GoogleNet also. You can see ResNet also. So, in ResNet also, there were ResNet 50, ResNet 150. How many layers are there? It is usually written. Now, when I'm talking about ResNet, I would like to emphasize one more thing. Res means residual. So there is ResNet 50. It means 50 layers or 152 layers. So how is there feedback or how is the residue taken? It is taken like if you have an X, there is a weight layer, then there is a ReLU. Like I told you, rectifier linear unit, you can add with an identity X. And this of feedback can be obtained, and ResNet is this architecture. Now, because I am talking about computational complexity, like I told you, 138 million parameters need to be computed. So, usually there is a memory bottleneck, and GPU is required for a few GB. So, if you just see the graph on the left side, you can see what is the accuracy which have been obtained versus this was 2017 paper. This is still 5 years back paper which I've taken. But this paper was also taking into account various complexities which are associated. So how much complex is VGA19 and how much complex is your Inception V3. Now, one more thing which can be seen is that there could be text to speech conversion also you can do apart from your speech recognition and speech other technologies. You can convert your text to speech. So how can you do that? You can use that, for example, if you have a Hindi language. So this small experiment was done. This is one of the case study. So what we did was we had to first use, this was an old paper and we were trying to get into that. So when Hindi language was given as input, we first converted into romanized script. That is, we converted our script to Hindi. Once it was written, then there was each phoneme, we had one particular sound associated with it, and then we had to concatenate it. But concatenating it was a challenge. Why? Like you must have heard in Indian Railways, train number 1, 2, 4. So there is a very distinct stop between two words after one syllable, because our speech technology has still not progressed up to that level. Whenever we are talking, we all have a prosody and we have natural stops. We don't speak in a robotic manner. Like if you even talk, whenever you speak even a single sentence, if I ask you to say, just say a train number, you will never say that the train number is. That whole sentence is very easily said. The train number is 1, 2. So that is not a, the concatenation was not done properly. So we were trying to use the concatenation, and deep learning algorithm was used so that it could merge the two phonemes easily. So at the moment, these are the few things. Is there anything else we can talk about or discuss?
Whatever you feel like, because we don't have questions till now in the chat box. So anything that you want to share, or maybe within a couple of minutes we may have some queries from the participants also, so that we can discuss.
That would be an excellent.
Yeah. So you made a very good presentation, giving the state of the art uh, in terms of the architecture, in terms of computational complexity, uh, and the comparative performance of different deep learning architectures. So it would have been very, very useful for the participants, and those references are important for them also, the name of the journal and the conferences which they can actually explore to see what is the further progress in this particular area.
Right. So, sir, the students have already the idea of what does it mean by supervised learning. For example, when we are talking about training data, so they must be having a quite detailed knowledge about what is supervised learning, what is semi-supervised learning,
uh,
what is unsupervised learning, all these things.
some of them may have, because we do have students as well as teaching faculty members, not only from engineering, plus they do have a background like maybe mathematics or statistics. So we have got a varied, but mostly from engineering background, electronics and computer engineering background. So most of them would have that idea. There is one question I can see in the chat box, is how can we use CNN for one dimensional data? This is a question from Mr. Yash Pratap Singh.
Okay, this is really a good question. So, let me show you a small snippet of what does an algorithm look like. Okay, so at the moment I have deleted that. No, I do have that slide. Let me show it that to you. So, if you can see this particular slide, I'll just remove the hiding part. And I'll put on the slideshow. So let me talk about how does it look like in the coding. In the coding, whenever you are doing it on Keras, if you are using a library Keras, there are various libraries. Like I told you, you do not need to define a particular library or a particular filter. If you are intending to use a convolution or deep learning network, there are various libraries that are fully established and are open network. So few of the examples are of the library are PyTorch, Keras. Okay. Now I am taking one example which is of Keras. Whenever you are doing some coding, so there would be a first point is how to do coding and what is the fundamental behind it. So instead of taking one dimensional, you can use one thing is that you can use when your speech is coming, you can put it in image form. For example, you want to make an image, you whenever you are speaking, your frame sizes of a particular let us suppose 5 or 10 milliseconds, and that 10 milliseconds is the frame. Instead of taking one frame at a time, you can very easily put 10 frames below it, and then you can have a matrix, two-dimensional matrix. So when you form your actually one signal, one dimensional speech signal into an matrix format or an image format, you can use this convolution 2D. This is an established keyword which is from the library. Whenever you start coding, if I can even show you examples for that, but not necessarily for image, not necessarily of speech. I have algorithm for images or biomedical signals. I'll show you for biomedical signal, in which there is a one dimensional data, and instead of using one dimensional data, I put it into a matrix format and I was using convolution 2D. So this is one way. Other way is you can use conv 1D also, and there are filters which are associated with that conv 1D also, which is available in the library. Am I clear? What am I trying to say?
Yeah,
If there is, for
yes,
example,
yes, yes.
this is a code in which convolution 2D is there, because I have this in my PPT, that is why I'm showing. If there is convolution 2D, then you need to specify how many number of filters are there. Then there are 25 filters which I'm using. And what is the dimension of that filter? It is 3 cross 3. Instead of this, if I would have used convolution 1D, then I would have, in the bracket, I would have taken 25, comma, instead of 3 cross 3, it would have been 1 cross 3 filter. Something of that sort. So one method was using convolution 1D. Other method is converting your one dimensional signal into a two-dimensional matrix and then applying convolution 2D. So these are the two ways in which you can do your deep learning.
Thank you, ma'am. But we have got another question from Miss Hira Javed. She is asking, ma'am, how can we use our data in transfer learning with VGG 16?
Okay, so you have used a new term which is called as transfer learning. So I hope you know the meaning of transfer learning. Transfer learning means you have already learned your parameters on other classifier, and then you are trying to use those parameters on a fresh new problem set. For example, you have learned the first problem set was differentiating between apple and mango. You trained the mango, and you trained on apple and mango. You obtained all the filter and parameters associated with it. You have learned those parameters, and then you want to modify. You have already done most of the homework. Now you want a new objective needs to be met, and that objective is to differentiate between, suppose, watermelon and pomegranate. So those parameters which was already used for apple, and there is no matching between those two problem statements. One was a different problem statement, another one was different parameters, but still, because the nature was same, that is why you were able to transfer your parameters from one problem set to another. So this is by this way you can do transfer learning. So, what was your exact question again?
The question was, can we use our data in transfer learning with VGG 16?
VGG 16 is one architecture which you have already learned. By training that, by using VGG 16 architecture, you now have parameters. Now those parameters can be used for another problem set.
Okay, we have got one question from Dr. Prashant Upadhyay. Why we do the dropout in CNN?
Okay, so like I was talking about, fully connected networks, each when there is a dropout, there is total connection. There is totally each in first layer to second layer. Suppose in the first layer there are 3 neurons, and in the other one there are 4 neurons. So each of those 3 neurons will be connected in every way possible way to another 4 neurons. But just calculate how many number of weights you have just now calculated. And after calculation, you are even storing those weights. So, how many parameters you can just calculate it, and you will know that these many number of parameters need to be stored. So, instead of that, if we just miss out few connections, first problem will be solved. That yes, my storing of weights or parameters will be saved. This is one reason. Another reason is overfitting. Suppose if I have learned something, I do not want that when my test data comes, when my new input set comes, I do not want that it should not be able to adjust to that. Whenever you want a generalized model. The more generalized it is, the better it is. You do not want your model to overfit. So, to reduce overfitting, dropout is the word. So that is the reason.
Okay, that thank you for the detailed explanation. We've got another question from Syed Abdullah Atiq. The question is it possible to hear the speech after concatenation done in your work?
That work was done quite a lot earlier. So yes, we the objective we were trying to achieve was that there should not be any disruption or any visible pause or any unnatural. So there are quite few objectives when you are learning about speech technology. So you must have already learned about it, or you are going to learn about it. There are few parameters or few objectives. There are two type of objectives. One is subjective. Subjective means that you a person hears it and then evaluates that whether this particular sound is correctly concatenated or not. And the other one is objective. So like when you say PNR ratio, signal to noise ratio. So what is this? You are actually putting it into formula. So when you are talking about speech, there are few objectives which needs to be met, and we were trying to achieve a higher accuracy using these algorithms.
Okay, I don't see further questions over here. So with this, probably we are at the end of the question answer session, and we are nearing the end of the time also for the 1 hour. So, as a token of appreciation, as we are in an online mode, I could only thank you and virtually send you this memento sort of thing. And I hope that in future we will surely invite you to get benefit from your experience and the new deep learning scenario which is coming up. I'm sure that it will be motivating our research scholars and young faculty members. So I would like to thank you very much for the enlightening talk and the time that you have taken out in such a short notice. It was really very nice and informative lecture for all of us. Thank you very much.
Thank you, sir. Thank you so much.
Uh, for the participants, we will have the next session. And as just now, you would have seen that we are now having some stopgap arrangement. So I will try to engage the next 1 hour again with a very short notice, but my core area not being exactly this. But anyway, I have tried to uh, make something out of which is related to speech and talk about some of those works that we earlier carried out, not a very recent work, but we will try to have a slightly different orientation now, which is about the imagined speech. So please stay tuned, and I'll try to go to the slide presentation mode. I hope the slide is visible to everybody.
Yes, sir.
Yes, sir.
Fine. So I am trying to give a overview of what we have done in the case of something which is related to brain computer interface and also related to speech, but this is not a spoken speech but imagined speech. So instead of actually speaking, we are actually trying to imagine what is to be spoken, and then we would try to decipher what we were trying to speak. This is not a full study, but just an introductory part of that. Of course, much is needed to be done in this particular area. So, this is how I will try to proceed and see that how much we can cover. Essentially, this is slightly deviating from the speech as such, but we will be talking about the brain signals. So I will be taking into consideration not the acoustic waveform, but the electrical activity of the brain. And therefore, there will be an overview of EEG signals that is actually captured from the brain. Or we will talk about, in general, brain imaging technologies, the techniques that are available. And then, as a case study, I will take up the imagined speech recognition, and then we will have the conclusion. So, if we see our basic human body, we do have the entire body as a, you can say, system, because as an engineer or a electrical engineer, we do have systems and subsystems. That similarly, this entire body is may be considered as having number of systems. For example, we have got a circulatory system, we have got a respiratory system, digestive system, and each system has got subsystems in them. So the subsystem, in the case of circulatory system, we may have the heart as one of those subsystems where the blood is circulating or one process is going on. That is, a physiological process is going on, and while that process is going on, various signals are actually generated. Some may be electrical, some may be magnetic, or some may be in the form of temperature or pressure. So all these signals gives us the health or the status of those subsystems, and we can actually analyze the entire system by looking at these signals. One of the very common example is that we look at the ECG, and then we talk about the ailment in the heart. Similarly, if we come to the speech, there's a speech production system that we have got, and the detail was given to you in the very first lecture by Professor Arun Kumar. He talked about the different types of articulators that we had, the jaw, the lip, the tongue, and we had the lung, which was actually a prime mover, which was pumping the air, and the air was going through the larynx, through that oral and nasal cavity, and then the acoustic signal was emitted. But and in the case of speech recognition that we have been talking about, or the speaker recognition, we actually collected the acoustic wave that was being generated. There has been attempts where people have tried to collect the muscle activity, EMG signal, and then they have tried to analyze the muscle activity and see which particular word was actually spoken. But if we go further down to the basic, we do know that all these organs, they are actually controlled by the brain itself. So when we are speaking, the movement of the articulators that are occurring, it is actually a signal which is coming from the brain and asking the lips or the mouth to perform action in a specific fashion, and that's what it does. This actually implies that the signal which is coming from the brain is again a unique signal to utter a specific word or utter a sound or a phoneme, and hence it may be possible that if I tap into the brain signal itself, I may be able to decipher that information from the brain signal, and instead of looking at acoustic signal, we can actually get information from the brain itself. A lot of applications like that, a person who has lost speech, if I can read it from the brain itself what he is trying to say, then I can have uh, a speech synthesizer which can actually take that information and then generate the speech. So these sort of applications may be developed. But of course, as we know that the complexity is much large when we are talking about the signal that we are getting from the brain, because the brain, apart from controlling this, has got many other activities, and the same region of the brain may be responsible for many activities. So in this particular talk, we will be just trying to have or design an experiment where we can look into the concept that whether we can have the recognition possible or not. In the case of brain computer interface, when we talk about, we have got two categories also present. One is when we are actually speaking, that means when the signal is given and the person is speaking, and the other possibility is that I am just imagining that I will speak. So that imagined speech, I am here talking about the imagined speech that we will be considering over here, because we have got the overt speech when we speak loudly and the other person is listening. So this is very, very easy, and this is what we are actually doing in the case of speech recognition. Whispered speech is having another complexity, a level of complexity, because uh, the sound level is pretty low, and the waveforms are not very clear, and it is having a lot of addition of the background noise also. So that becomes more difficult. And the third is the imagined speech, when a person is actually just imagining the sound he is producing, and then that sound is actually interpreted by a computing device, and that can be actually typed in or the action can be performed. A very simple application, for example, is that you are just watching the television in your room, and then you think that, okay, now I should switch in the change the channel, and I should now, because it is nearing 9, I should watch the news. So just you imagine that, and the action takes place. Or you imagine that the temperature, the cooling of the room is not adequate, the temperature has to be reduced further. So you are imagining, you are not using your remote, but just imagining, and the action actually takes place. So this is what reading from the mind, that's what it is coming up. Now when we talk about this, we need to look into the techniques by which we can get information from the brain. The most common techniques that we will look into, because we are talking about brain computer interface, then we should take into consideration some of those basic requirement of those applications as well, because uh, those requirement will be that the signal that we acquire should be easily acquired. The device should not be very bulky. It should be portable. It should not be very costly. And the data that we get is of good quality as well. So the electroencephalogram is one of those techniques by which we try to look into the electrical activity of the brain, that is the firing of the neurons in the brain, and the electrodes are placed on the surface or the scalp, and the signal is collected, and we may process that signal. Of course, these signals are analog in nature, so we need to do appropriate conversion, sampling, and then amplification. This is what we will be talking about. The second option is magnetoencephalography. That means we are having the magnetic imaging of the brain itself, as the image shows that the device is pretty bulky, expensive to operate. So this may not be very useful in our application that we are talking about. Electrocardiography is a technique by which we use electrodes which are implanted inside the brain. Usually we use microelectrodes in that, but this is a very complex procedure in which a surgical intervention is required. And the operation is to be, or surgery is to be carried out, and the brain, within the brain, the electrodes are implanted. Sometimes it is also known as IEEG, that is intracranial EEG, also known as the depth recording, uh, where these will be implanted. The advantage of this technique is that because we are now collecting signals directly or very close from the source itself, the signal quality is good, the noise interference is less, and hence the signal to noise ratio is much higher. And because microelectrodes are used, then the localization of the signal is much better. But the major challenge is the implant itself. So this is a difficult procedure. The other commonly used technique is the functional magnetic resonance imaging. Of course, this is again a very complex and expensive, although it is non-invasive technique, but it has got a slightly different function, that we get images from the brain. And for the case of brain computer interface or the imagined speech recognition task to be practical, of course, this imaging technique is not among the list of favorites. Then we have got another technique which is nowadays becoming more popular, is the near infrared spectroscopy, or the functional near infrared spectroscopy, where the infrared light, which is in the range of 700 to 900 nanometers, this is used, and the absorption of the light by the hemoglobin, that is the presence of the blood, uh, how much amount it is being absorbed. So from that information, we can get that which area of the brain is active, because the active area will have more blood, oxygenated blood over there. So that becomes more active. And hence we can actually know, when I am performing a specific task, which area is active. So based upon the different active area of the brain, we can get some information as the waveform is shown over here. So from these waveforms, we can get some information that what is the task being performed, and we can actually train our classifiers that we have been talking about since the beginning using these things. If we look at the comparative analysis, this is important that there are some things which be required in one application or some other parameters in other application. For example, when we are talking about brain computer interface or the imagined speech recognition, I would like that the temporal resolution should be high. Temporal resolution means that in time, how quickly I can resolve between two different samples. So it actually may vary. The value that is written over here, it actually depends upon the sampling frequency that we have got. So we can have higher sampling frequencies and we can have better temporal resolution. Spatial resolution is within the space or the structure of the brain that we are having, how much closely those activities I can resolve. The higher the spatial resolution, the better it is. So EEG is not very good in the case of spatial resolution unless and until we increase the number of electrodes, but it is non-invasive and portable. MEG is having good temporal resolution, good spatial resolution, non-invasive, but it is not portable at all. ECOG, that is the depth recording that we were having, the IEEG, it is having very good temporal resolution and of course better spatial resolution because we are using microelectrodes. But the major challenge over here is that this is invasive, although it may be portable. So this has got major limitation unless and until we have got major breakthrough in surgery or brain surgery. This technique may not be a very common technique. fMRI or FNRI, all these are actually looking into the metabolic activities of the brain that is going on. Temporal resolution is not very high over here. So this is the major limitation. Although we may have better spatial resolution, both of them are non-invasive, but fMRI is not portable. As I told you that FNRIS is a portable technique which is also in competition with the EEG as well. So this is just the overview of what actually happens in the brain. We do have billions of about 85, 86 to 90 billion neurons in the brain, which are active, and many of them are firing simultaneously, generating certain electrical signals or brain waves. And because of those, there is a voltage fluctuation which can be actually detected by the electrodes. So we actually try to detect those electrical signals, and it was, if we go back in history, it was the German physicist, psychiatrist Hans Berger in 1924 who just coined this term electroencephalogram, and he actually showed also that these signals are slightly different when the person is sleeping or when the person is having some epileptic attacks. So he used or generated or recorded those EEG signals and published some of his work. That was way back in 1920s. So we have got about 100-year old technique which is now being used, of course, in a lot of diagnostic purposes, as well as has got a lot of engineering applications as well. So if we go into the slight details of the brain essentially has got four lobes. That is the frontal lobe. If I want to do analysis of a person, what is the personality, what is the emotional status, uh, then the frontal lobe information is very important. And if we collect signal from the frontal lobe, we will be getting information related to that. Then we have got the parietal lobe, which is about the cognition and mathematical abilities in a person, and the memory, the normal verbal memory, which is there. The occipital region, which is at the back of the head, is actually responsible for the vision that we are having, the colors that we actually see, the shape, and the movement. Similarly, temporal region, which will be our focus over here, is for the speech and auditory processing, so language comprehension and long-term memory. We saw in the first lecture that the hearing, human hearing, how the human hearing was with different frequencies. And if you go into the details of that, you will find that the acoustic signal which enters into the ear, it actually goes into the cochlea, and it vibrates the hair cells, where from the auditory nerves develop certain potential, and these nerves actually terminate in this temporal area, which will generate different voltages corresponding to different frequencies. The cochlea is actually a distributed filter which actually generates different potential at different frequencies. So it is roughly doing a spectral analysis of the audio signal, which is then converted into electrical signal and transferred to the brain. So that perception part is also there in the temporal region, as well as when we are speaking also, it is governed by the temporal region. So this is an important region when we talk about the imagined speech recognition. Going to the a bit more technical details about the EEG signal, as we know that ECG has got a specific standard lead connection pattern. Similarly, we do have a specific pattern for the case of EEG data collection, which is also known as the 1020 system, which is shown in the figure. The 2 points are identified, that is just above the nose, the dip that is there, that is nasal, and the inion at the back of the head. This entire length is divided into 10, 20 percentage terms, which is shown over here in the figure. And these distribution, according to that, these electrodes are placed. And nowadays we do have electrode caps which a person can hear, and there are slots where you can insert those electrodes and the signal may be collected. But otherwise, we need to do a manual measurement and place those electrodes as we usually do in the case of ECG. But these electrodes are slightly different and more sensitive, because the signal level that we do encounter in the case of EEG is in the range of microvolts as shown there. And specific numbering scheme is being followed. The left hemisphere, as it can be seen that we have got specific FP1, FP7, F3, and all those numbers, all the odd numbers one side, left side, even numbers on the right side. F corresponds to the frontal region, C is the central, O is the occipital, P is the parietal region, T is the temporal region. So all those regions are being mentioned, and accordingly the signals are connected. So we will have, based upon the number of electrodes, we may have that many number of channels. Usually 8 is the minimum number of channels used for the diagnostic purposes, or most of those BCI applications, we may have as small as only two channels or three channels, or in some cases, single channel EEG recording can be done. For example, in the case of sleep analysis, when you do so, single channel recording may be carried out along with other physiological signals. Now, if we look at the EEG waveform and try to identify different bands, we do find some distinct bands that are delta, theta, alpha, beta, gamma. There may be some more classification, high and low beta, all those sort of finer classifications may be there, but these are the most commonly used classification. Delta band, which is a very low frequency, we are talking about less than 4 hertz, and this is the highest amplitude waveform when a person is in very deep sleep. So this EEG signal can be detected when the person is in a REM sleep or deep sleep. Then these waveform will be appearing. The theta waveform, which is from 4 to 8 hertz, these margins or the ranges that are specified over here, somewhere you may find it is 7.5, somewhere 8, somewhere from the ranges may be slightly different. Alpha wave may be 8 to 16 in some places. So we don't have a very strict demarcation, but this is roughly the range which is there. So if a person is drowsy, then we may have theta wave present over there, or a person is in wakeful state, eyes closed, then we have got alpha activity. A person is busy and concentrating, so beta activity, or a person is in consciousness and very active attention, he is paying attention to a specific work or task, then these high frequency oscillations also come into picture, but they are low in magnitude. So based upon these things, these are the major observations that have been noted down, and hence it was observed that uh, some of those effects were reproducible, which could be seen in the EEG, and hence it was suggested that probably it can be used for diagnosis as well as for some engineering applications like brain computer interface, uh, where we can use it for people with spine injuries, or we can have some brain control gaming also coming up. But there are some issues, important issues that are to be addressed as well. Most important is uh, the artifacts that we actually encounter when a person blinks the eye. Then this is a muscle activity which is in the millivolt range, and the EEG signal is in the microvolt range. So now as soon as there is a muscle activity near the electrode, it will cause a huge interference, and during that time you won't be able to see those electrical activity of the EEG signal unless and until proper filtering is being carried out. A person is swallowing, or a person is sweating, so all these effects will be changing the EEG, and hence the data collection becomes a very challenging task. Further, if somebody is trying to collect the data for the EEG task, then whether the person is motivated or not. If he is not motivated, then I will have a different EEG activity. If he is motivated, then I may have a different activity. Now, coming to the case study that I'll be discussing is the work which we actually published in 2015. We had some more publications, but mainly conferences publication. Unfortunately, the student who actually started working in this area, she was offered PhD in UK outside India, so she moved over there, and therefore we couldn't continue, and we didn't had later on takers on this particular project. But this work was carried out on a already available database which was collected in Japan from three healthy subjects, one female and two male. It was a simple task, and in which a vowel was actually to be pronounced just by opening the mouth. The sound was not to be produced, but just doing the action and having the intention. And then oo, when the lips are rounded. So these two actions and the imagination that I am speaking this sound, but without actually having the sound being produced. So just imagining and doing the action. So it was a sort of mime thing that was being done, and the data was collected. So this is the reference of the data also given over here, which is actually freely available and can be downloaded as well. So if you go into the bit more detail about what was the protocol of the data collection, it was actually a audible beep in the first 2 seconds, and then in the next second after the beep, the subject has to imagine either a or oo, or he has to keep rest and relax after that. So these were the, you can say, three tasks were there: a, oo, and rest, and correspondingly 3 second EEG recording was actually carried out for the three subjects that were there in the trial. So if you see this, uh, this was the screen which was actually used for the subject. A fixation cross was there. So when the beep was there for the first 2 seconds, this cross appeared, and then when a pattern appeared, that means the lip was open, and the subject was supposed to imagine this and do this action. And oo when occurred, and then the third was that was no action was to be taken, that was the control one. So these patterns appeared once, and then it was a rest interval, and then again another trial. So there were number of trials which were actually carried out, and based upon those trials, the data were collected using a 1020 electrode placement system, and the sampling frequency was pretty high, 2 kilohertz usually, which is not done, but to collect good data, this was carried out. But later on, it was down sampled to 256 hertz. Reason being that we usually have to stick to very low frequencies below 50 hertz. So 250 hertz sampling frequency would be good enough to analyze the outcome of the results. So this was actually the scheme that we actually followed. That means the data was already available. We performed some pre-processing, feature extraction, and then classification. I'll talk about the pre-processing step, feature extraction a bit, classification. I'll just give you the results, and if the time permits, we may talk about some problems in the classification, if at all the time is there. So in the pre-processing, we actually performed was band pass filtering. Usually when the signal is acquired, there is some sort of DC wandering present if the amplifier is not very good, and that has to be removed. So band pass filtering of 1 hertz to 45 hertz. This was the pass band which was used. And this will also remove high frequency artifacts, that is 60 to 72 hertz artifacts, which is coming from ECG. We do have major problem with power line interference. Depending upon where this recording has been carried out, it will be 60 hertz or 50 hertz. EMG signal will be above 45 hertz, so that's why it was just kept 45 hertz only. And then 4 channels were selected. There were total 50 trials for each task. So there were actually 3 subjects, 150 trials, and then we did divide into training and testing pattern. But before that, we did the feature extraction process. Uh, this actually shows the feature extraction process. How do we carry out the feature extraction process? Uh, we use a small window in which the feature E1 will be extracted. And then the window that was used was actually a simple rectangular window, which was non-overlapping. So this keeps on going till the end of the recording that we were having. And because we have got a number of channels, in this specific case, we were having only 4 channels, but we may have more number of channels. So we may have recording and the matrix, and which may be something like this. And we may then apply certain dimensional reduction technique in which we may reduce the number of features, because it will have the number equal to the total number of channels that we are having. So we may take the average value of the feature or the mean value of the feature, one specific features. So like this, we may have many features that we can extract and then construct a feature vector. In this specific case study that we are talking about, we tried to have a wavelet transform decomposition. Reason being that usually the signal that we encounter is EEG, non-stationary in nature. So because of the non-stationary nature, it is not very suitable for the Fourier analysis or short-time Fourier analysis, and therefore we went for the wavelet analysis, in which different levels of decomposition was carried out, as it is shown over here, that we performed the 4-level decomposition, and the levels which are marked, the frequency band which are marked as black were actually chosen. Reason being that these are the important frequencies or frequency bands which have been reported to give good performance in the case of imagined speech. Therefore, these bands were actually selected. This was a dyadic discrete wavelet transform which was used. And then from these 3 bands, features like the average value, the variance, the skewness, the kurtosis, and the geometric mean, the harmonic mean, interquartile range, then the energy, entropy, standard deviation, and waveform length. These 11 features were actually calculated from each of these bands. Some of those features, the formula is shown over here. Others I have not written. A simple energy calculation, kurtosis, entropy. These were the calculation, but these calculations were performed in each of those bands, and then the features were actually ranked or it was actually selected from the set of features that we got, which was 11 into 3, that is 33 features. In the feature selection, various techniques can be used, uh, which is important in the case of machine learning. So this will be useful when we have got a lot of feature and we want to go for which features to be selected. There are three main types of selection criteria which is being followed. One is the filter type, in which the feature are measured in terms of their importance, such as the variance in the features that is there. So how much uncorrelated they are the to each other. So based upon these information, some of those statistical information may be used to know the quality of the feature and then rank them. Other possibility, that is the wrapper type selection, is where we may grow or we may reduce. That means we may start with a single feature and we keep on adding features and see how the model is performing. And then we do find that after a certain number of features, the performance of the model will not improve and it may also start reducing. So we may stop at that particular point where the optimum performance is achieved. It may be the other way around, that we may start with maximum number of features and then we start removing them and see where the optimum performance is achieved. So this is where we will have the optimum number of features. Of course, this will result into a different feature set as compared to the first one. And in the last one, this is the more complex one, where the feature importance or the relevance is actually explored with reference to the model that we are having. So it is a joint process where the feature importance for a specific model is being judged, because it is possible that one feature may perform good for one specific model, the same may not perform good for the other specific model. So it will be particularly when you are using a model and training that and going through the learning process, which feature gives the best performance, it is being ranked. But then this is a slower process and it is time consuming, but this gives the best result, of course. Uh, if we look at the different types or the schemes that are used, that is filter type is minimum redundancy, maximum relevance algorithm. Then we may have neighborhood component analysis, relief F algorithm. These are the standard algorithms which are used in the filter type. Then the wrapper type is adding features sequentially or removing. These are standard procedure. And then embedding type, we may have linear regression or bagged classification or regression of the ensemble classifiers.
Hello.
If we look at those rankings, we do find that if the features are highly ranked, these two features have been shown over here. Just as an example, the blue one and the reddish one. I am not very good in color identification, so I think that it is nearest to red. So these two can be seen as separated, and the low ranked feature, as you can see the below one, they do show a lot of overlapping, which is obviously the case that when we try to use them in a classifier, this will result into poor performance. So the ranking actually helps us to identify those features, reduce number of features, and then we can use them in training and classification. This slide you have gone through. So what we actually did in this case, and we compared it with the person Dasala from Japan, who was actually the originator of this database, and he published his work. So we compared our work with his work for subject specific uh, recognition or classification task, which was a pairwise classification. Pairwise classification actually means that we were trying to differentiate between two pairs, R sound, when the person was imagining, the subject was imagining an R sound, and the person was having a rest. Similarly, oo sound and then rest, and whether we were able to differentiate between A and oo or not. For those cases, if we see, we can see that the accuracy that we achieved were uh, nearing 80s. Of course, was a very limited, very small, low scale experiment which was carried out, in which three class problem was only explored, but that was way back, and now we do have a lot of development uh, in the computation as well as in the understanding of the EEG signal, as well as the quality of acquisition of the EEG signal. So now people have done much better work recently. But as I told you that I was having a very short time, and I started this presentation just in the afternoon along with other technical issues that we were having. So this was what I wanted to share with you.
Yeah.
Maybe we can have questions, or I do have some more thing, but then that this is not very much related to this. One problem that we could talk about is the bias variance problem. But if there are questions, we can talk about questions over here related to this work.
Yeah, there's one question in the chat box. If we do the analysis of psychiatric disorder, so which band of frequency is taken into consideration?
Psychiatric disorder. Uh, See, this is from Dr. Prashant actually, but as I told you that we have not done a lot of work in this psychiatric disorder. Maybe I am not sure about the frequency band. We have to look into those signals and then analyze, because psychiatry means maybe sometimes the person is very much gloomy and sad, and therefore we may look into the emotional status, that is the frontal region, and if he is not very active and agile, low frequency band, that is maybe delta band may be very important, or uh, theta band, which is 4 to 8 hertz frequency, that may be relevant for the analysis. But I cannot for sure say that. This is my guess based upon the person. But a psychiatric disorder may vary, and maybe the clinicians may be in a better position to talk about the symptoms, because the symptoms may be very, very different. So what I was just trying to expose you with is a totally new dimension in the speech recognition area, which is imagined speech, where you can say that maybe after some time you may say that I will be reading one's mind. So mind reading and all those things are now very, very popular, but this may become a science where you can have certain implants or certain electrodes being placed, and you get the signal, and you can actually then read what is there inside the mind.
Okay, so Yash Pratap is saying it was so informative and new concept to me. Thank you, sir. Okay, if any participant is having any question, okay, so you can ask using a microphone if you wish.
No, if you want, I can continue with some of the slides that I have got. But that is actually some of those more mathematical, or more of the conceptual steps which are there in the machine learning. May not be total application, but may be concepts. about bagging and boosting and all those things, and the problem of bias and variance that we do encounter in the case when we are training.
Maybe 10 minutes or 15 minutes. That just a concept. And but one announcement I want to make here.
Yes.
Tomorrow, a lecture is scheduled by Dr. Hemlata Maheshwari, and the request from the speaker is that participants are requested to use earphones or headphones for the demonstration, because she's from industry and she want to demonstrate some product, actually whatever they have developed, it's R&D product. So for that, she want that participants should use, instead of using open speakers, instead of that they should use earphones, means, or headphone. So that was just an information. So tomorrow when you will be joining, please carry that with you. Yes, sir.
Okay.
Maybe only for 10 minutes you can discuss if
Maybe yes.
bias and overfitting.
I'm not going into the presentation mode. Then I will
Yeah,
just, because
it will be good if, yeah.
because right. So this is actually when we are doing the training process. We do encounter a lot of problems, and then we try to explore that what is to be done. This is one of the major problem which we do encounter. That is on the y-axis, if we see classification error, and uh, we have got training and the validation data which we do find. So underfitting and overfitting which is occurring, how do we actually avoid these problems? Now, if we try to realize what is happening, what I have shown in this particular slide is the blue one is the error surface. The center of the error surface is actually the minimum error, and the line that we are having, the black line, is we are iterating and trying to reach to the minimum error of the training data. Now the validation data is shown in red, which is having a slightly different error surface. Now why this error surface is different? Reason being that the distribution that we have got of the training data is not exactly the same as that of the validation data. So we do have a slightly different, because we statistically try to reduce the error. So at this point, yellow point, when we are over here, we can see that the validation error has reduced, but the training error has not reduced, and we keep on iterating, and therefore the validation error actually goes higher and higher, and our training error reduces. This is what is happening physically when we are trying to uh, overfit or train our machine learning model to the specific data that we are having. So when we do these sort of things, then we end up with two basic things. One is that when we have got the performance, that is, we are hitting the bullseye, the red area, with the result which is actually blue dots that is shown over here. So low bias and no low variance model, that means we are having the perfect scenario where all the results that we are getting are actually in the correct region. But when the data that we are having is having high variance, then we may have the result which is not actually at the minimum error, but the error is scattered around that. If we try to calculate the average error, of course, we may get average error equal to 0, but the absolute or the mean square error is always high. So this is because the variance in the data is high, and you have trained your model, and the model was on the training data on the bull's eye, but because of high variance, the test and the validation data was having large variance, so you are not getting that result being replicated. So this is because I have overfitted my model with the training data, and hence I need to look into certain stopping criteria or certain other technique by which I can avoid overfitting. Then the third one is the high bias, low variance. Now the variance is low itself. That means I am always able to make a decision, but that decision is having a huge offset from the desired value. Now this actually means that I have got a problem in my model itself. The classifier model that I am having is not able to properly uh, reach the minimum error. It may be the reason that I have taken a very simple classifier. It is possible that it was only a linear classifier and I could not have a good approximation by the linear classifier, therefore I had an offset. So if I have got this sort of problem, that the offset is there, although all the points that I am getting, or the cluster that I am getting is very compact, this actually means that I have to think about my model itself. I have to change my model. I may have to increase the complexity of the model itself. And of course, the third one is the worst case, which is showing that the data is totally scattered, which is having a bias also, lot of offset and high variance as well. So this is giving us some idea about what is happening during the training process. Now, if we look at the model complexity and the error, I have not done all those mathematics. It comes out to be a bias square. But anyway, this bias that we are getting, if we have got the bias error reducing, this will be only the case when we are increasing the model complexity. Less complex model will usually result into higher errors. And I may have high variance because of the model complexity, because the model may be trained specifically for the training data itself. So we need to actually have an optimum point somewhere over here for the model complexity, such that the error is not very high or the model complexity is not very high. Usually we may have two possibilities, training and test error, which is shown over here. One is the regime 1, where we can see that we have set an acceptable threshold of epsilon, and in the regime 1 or this region, first region, the training error is very low, but the test error is high. In the second region, we do find that both the training as well as the test error is high. So we need to look into this issue. And in the case of first case, why we are having high error is because we may have high variance. And high variance means that we will try to solve this by adding more training data. If the data is more, then we will have a better representation. We may reduce the model complexity, or we may go for a technique which is known as bagging. The other possibility, that the region 2 that was there, where the error was high in both the cases, the training and the testing, it was higher than the threshold that was specified. So this is because there was high bias, and therefore we need to have more complex model, or the features that we were having were not able to properly classify them for that model complexity. So we may need some more features, or maybe boosting. So bagging and boosting, these are the techniques. Bagging, I will just talk about this and then maybe I'll stop. This is the technique which was proposed, uh, which actually has three steps, in which the original data is actually resampled into different number of sub data groups that we are having, and we draw the from the original data with the replacement, and we create subsets, and these subsets are used to train classifier. So a bootstrapping process is being carried out from the original data, and we may have n number of sub data being created from the original data, and we have got n classifiers trained on these individual data, and then we aggregate the results that we get, and therefore these aggregation process is that is the ensembling. Overall it is known as the bagging process that is being carried out. So we average out the performance that we are getting, or we take the majority logic or voting over here. Of course this is an expensive thing because we will be having number of classifiers that are to be implemented, becomes more complex. Another major problem is that the interpretation of the result is not straightforward. Interpretability is finished in this particular case. But of course, this improves upon the performance because this will reduce the problem of variance that was there and average out the result, and overall maybe slightly improve the performance. So I am that was the time, that was 9 I was given, so I have just reached that time.
Yes, sir. Thanks. So, if anyone want to ask any quick question you can take. Okay. I think now we can conclude today.
Okay, then thank you for tolerating me for about an hour or so.
No, no, sir, it was very informative. Actually, although it's all linked with the speech and it's a new dimension you have discussed, actually, imagined speech.
But we didn't had a lot of work over there, so
Yeah,
it was
it's a new direction for research, actually.
just introduction, so that people, if they are thinking of doing something, may explore this area as well.
Yeah, that's very challenging also.
That
The
is
area is really very challenging and very interesting as well. Yeah.
so.
So I think, sir, now we can end the meeting, and
Okay,
tomorrow we'll continue.
okay then.
Thanking you very much.
Thank you, everyone.